Hi everybody and welcome to the CERIAS Security Seminar. Today's speaker is Meenakshi Gupta. She comes from Indiana University and today she's going to talk about spoofing resistant packet routing for the internet.
Great, thanks. So I didn't know this was actually a class, so why don't we just...
Hi everybody and welcome to the CERIAS Security Seminar. Today's speaker is Meenakshi Gupta. She comes from Indiana University. And today she's going to talk about spoofing resistant packet routing for the internet.
Great, thanks. So I didn't know this was actually a class, so why don't we just do it the way I would normally teach a class? Raise your hand whenever you have a question. Please feel free to interrupt. If you feel like I'm not explaining something or something is not clear, we don't have to move forward at all. Sounds good? So I will talk about IP spoofing in the internet in general, and one of the approaches that we have pursued with my student Craig Shue. So this is about spoofing resistant packet routing for the internet. Basically, here are the three parts to the talk. I would first talk about what IP spoofing is and what kind of approaches are generally pursued in order to solve the problem. In part two, I'll discuss what is our approach to the problem and some evaluation on why we think the solution is actually practical. So IP spoofing in general is the forgery of source IP addresses in the internet packets. So the internet packets contain both source IP addresses and destination IP addresses. And the routers are mainly concerned with the destination IP address of the packet, and they do not concern themselves with the source address contained in the packet. Hence, if the sender of the packet doesn't really intend to do a two-way communication like you would in the case of an email transfer, for example, which involves multiple packets and a TCP handshake ahead of the time, then you actually could put any source address in a packet as you want. And this has been often exploited in launching denial of service attacks, and I'll mention a little bit more about it in a minute. So just to put IP spoofing in action, here's a snapshot of the network that you see on the screen, and this host on the left, which is 1.2.3.4, wants to send a packet that basically, it wants the packet to look like it came from 5.6.7.8. And it sends it to 9.10.11.12. So here's the sneaky packet. And when 9.10.11.12 receives this packet, it has no idea who sent it, and it thinks 5.6.7.8 sent the packet. Of course, if the host on the right actually tries to communicate back to the sender of the packet, then who would receive the reply? That would be 5.6.7.8, and that's essentially the problem of spoofing. Now, why is spoofing an interesting problem? What could you do with spoofing? And that's essentially why we are interested in solving the problem. So spoofing allows the attackers to conceal their identities, because at this point, when a host receives the packet, it has no idea who actually sent it. It only thinks someone sent it and who wasn't the sender anyway. And this is often used if a botnet, like a network of compromised machine, is used to launch a denial of service attack, then spoofing would often be used to protect the botnet. Of course, if you're using the botnet to send spam, then you would not be able to use spoofing. Is that obvious? Right? Because spam means SMTP connection, which means a TCP SYN packet comes by, a SYN ACK comes by, then you do another ACK, which means that you have to have a two-way communication link before you can even start to transmit the SMTP data. So if you are using the botnet to send spam, then you could not do spoofing. Spoofing is only applicable for denial of service attacks of the type TCP SYN. For example, you want to attack bestbuy.com. You create these packets that are coming from all possible sources on the internet, and these packets get to the host, and the host wants to respond back thinking you're trying to do a TCP SYN connection. And of course, the responses are scattered all over the internet because they're not actually sent from where they're claiming to be sent from. which means that a TCP, a server, for example, Best Buy, is actually sitting with all these connection requests in its table, thinking that it would actually hear back from the client, and it never hears back. Eventually, it times out, but if you continue to do that, its connection table is being utilized or used by attackers, and no legitimate clients can get through. And there's also reflector attack, which I won't go into the details of. But essentially, the point is that you can use IP spoofing to launch denial of service attacks. And IP spoofing is nothing but the act of putting a random or a targeted IP address in the source IP address in an IP packet. But you don't care what the source is, or maybe you put someone else's information, not yours. Right? Question.
How is it more damaging if a botnet simulates, say, 5 times its size or much larger its size?
How is it more damaging? Okay.
It says by simulating a larger fleet of machines, it amplifies the damage. How is that?
So let's say you have 5 machines and you're using those 5 machines to launch a denial of service attack. If you were only using your own IP addresses, let's say we are attacking bestbuy.com. You're using your own IP addresses, so you generate 5 packets, and now bestbuy.com has a connection table where it says, okay, IP address 1, IP address 2, 3, 4, 5 want to establish a connection with me, and I'm going to send a reply to the TCP SYN packets, which would be a SYN plus ACK packet, and wait for that the acknowledgement for that to come back. You're not going to receive the acknowledgement because they don't intend to reply to you. So you have occupied that much space in their connection table. However, if Best Buy had space for 100 connections, the other 95 connections could be used by someone else. But if those 5 machines first go as someone at Purdue, then go as someone at Indiana, then someone at IU, etc., then you could pretend to be 100,000 people trying to connect. So ensuring that at any point of time, the 100 connections that Best Buy can support are yours, just consuming their connection, space in their connection table, and hence just not allowing anyone else to get through. Does that make sense? How a basic denial of service attack can be launched, and it's much more damaging if you just if you use IP spoofing. However, if you were not using IP spoofing, then if you had a fleet of 5 machines, you could still simulate only 5 machines, right? There's this other side to it. For spoofing prevention is good for denial of service prevention. However, you could not prevent denial of service by just doing spoofing prevention. For example, today's practically all the spam we receive, including the phishing attacks that we see, are actually launched by bots. These are typically compromised home user machines. They have no idea their machine is a bot, and it's sending out spam. It's easier to shut down a botnet because spam actually has to use a valid source address and the correct source address, not just a valid one, the correct source address, which means you can actually use logs from who sent packets, etc., to shut down a botnet. And that is usually done. So if you try to follow links in your emails, for example, they would typically ask you to go to a web page, for example, in a phishing attack, and you try to follow that email. It won't be, that link in that email would not be valid after 5 days or so, because botnets are often shut down quite quickly. But if a botnet was used to launch denial of service attack, they can actually use legitimate IP addresses and still do denial of service attacks. So spoofing prevention will not prevent that kind of denial of service attack. But in that case, if they're using their legitimate IP addresses, you can at least shut them down the way you shut down spammers today. So in general, the current approaches that are used to prevent IP spoofing, or that have been proposed to do IP spoofing, fall in sort of 3 broad categories. The first is traceback. In this approach, basically the routers help in detecting the actual path a packet took. For example, in the picture that I showed earlier, if the path of the packet was not as if the packet was coming from what it was claiming to be. If the packet was coming from place X, but it was actually coming from Y, it would most likely take a different path. In the picture I showed, it would actually take the same router path, right? If you can detect the exact path of that a packet took, you can detect who the spoofer is with some probability, right? Does that make sense? A packet containing a valid source address has to traverse a certain path because that's how the routing protocol is set up. If the packet claims to be coming from somewhere else, it would take a quite different path in order to reach the destination. However, if the end host had some information that would help it detect the exact path that a packet took, then it can still detect, it can still say who sent the spoofed packet. Is that obvious? Does that make sense? Right? However, this does not help you stop anything. This only helps you find out where the packet actually came from, and maybe you can use it in your law enforcement or otherwise. So traceback approaches, there has been a lot of work in this area. In fact, in general, in IP spoofing prevention, this is the area that has received the most attention, which is that you want to trace the path the packets took rather than trusting its source address. And then you can use this information for apprehending the attacker. The other approach is mitigation, where let's say the source network and the destination network ahead of time exchange a key of some sort. It could be a simple text key, which means that every time the source network communicates with the destination, it is going to use that particular byte pattern, for example, bit pattern in its packets. If that bit pattern isn't known to other people, then no one could spoof that source to this destination. No one could do that, right? No? If I tell you whenever I'll talk to you, I will always end my sentence with I like you, right? Which means that if no one else knows our code word and they're not hearing us, then they don't know what my code word is. So if they try to talk to you as me, they would most likely not have I like you at the end of it. And you can detect it. However, this is happening at the source and destination networks, which means that the routers in between are, one, not concerned or not bothered with this whole approach, which is good, but at the same time, you're not preventing the routers from delivering bad packets. So the spoof packets will start from the source network, they'll traverse all the way to the destination, and they get dropped because the destination realizes that if I actually was hearing from this source, then the packets would contain some information that they don't contain. So you can prevent spoofing that way. You can prevent the destination network from receiving spoofed packets if it ahead of time exchanges the byte pattern or the bit pattern that packets from that source network will always contain, right? The third approach is prevention. What if we don't let the spoof packets from getting into the network at all? And this is essentially the approach we are trying to pursue too. There are several works in this area, but the prominent ones is where you do ingress filtering. So let's look at an example of ingress filtering because that is what we build on in our approach. So here's the same network. And again, this host on this red host is trying to send traffic as if it came from 5.6.7.8. So here's the sneaky packet, and the router has information about which interface the packet could come from. So it knows that in this case it's much it may actually have to rely on hardware addresses because they are on the same interface. However, in general, routers in the network know like what IP addresses are assigned to what hosts are sending packets, and they know if the host is not sending the correct source address in its packet, right?
What about mobile IP? Like if you have mobile IP, it's local, right?
If you have mobile IP, then where are you at this point? You are somewhere else, and your home agent is sending the packet, right? So if you have mobile IP, then okay, no, that's not true that it won't work. See, in mobile IP, even though you have gone ahead and acquired a completely new IP address in some other part of the network, your packet always first gets delivered to your home network, right? That's how it gets tunneled to the destination network, which means that, okay, actually let me backtrack for a second. This is happening at the source. So the sender of the mobile IP packet, it's actually completely independent of whether you're using mobile IP or static IP. It doesn't matter. The sender of the packet is responsible for guaranteeing that the IP address is not, that the source IP address contained in the packet is not spoofed. In particular, the router that is connecting the hosts is responsible for guarantees that my hosts are not sending spoofed packets. So you could be using mobile IP at the destination, or you could be using static IP. It is completely independent. Does that make sense? So this approach is good if everyone in the internet, by everyone I mean routers, if every router in the internet knew who it was connected to and ensured that in the packets they generate, they are putting in the IP addresses that they should be putting in. There is no IP spoofing problem in the internet, and that is an ideal solution, right? However, given that you cannot impose, practically you cannot impose anything in the internet, which means some people are going to deploy it, some people are not going to deploy it. If a network deploys ingress filtering and another network does not deploy it, the network that doesn't deploy can still spoof the network that is deploying it, because no one controls what you put in what network Y, who's not deploying, puts in its packets. And if network X is deploying it, it could still get spoofed, as in someone else can spoof its address range. Is that clear? So here, of course, the router denies it because it knows who can come. So the main shortcoming of this approach is that in the case of partial deployment, you cannot, in the case of partial deployment, those who are deploying get nothing to deploy it. They have no incentive for deploying this thing. So what could we do to provide them with some incentive to deploy? And that's essentially what our approach tries to do. So every router, every deploying router would perform ingress filtering, which means it takes responsibility for the correctness of the source addresses that go in the packet that it routes, right? And it puts a simple pattern, like a bit pattern. You can think of it as a 64-bit pattern or 32 bits, etc., to indicate that this packet has the correct source IP address. The next deploying router, every other router in the internet just does routing the way it would do today. If they weren't deploying it, they would not be concerned with the extra marking that's contained in the packet. But if they were deploying it, in that case, they verify the marking. How do they verify? That's a question, right? Which I'll answer next. They verify the marking and they say, okay, I have verified this marking and I will now put my marking in it. Why do you want to change the marking? You want to change it because so that you only have to know the markings of routers in your neighborhood and you don't have to be concerned with markings of the entire network, of the entire internet, right? So you verify the next deploying router verifies the marking, replaces it with its own marking. Every deploying router along the way to the destination continues to do the same thing. However, in order to ensure that the hosts do not receive these marking, the last router removes the marking. Now, there are two questions you should have at the end of this. One is, how is a router in the internet learning the markings of its neighbors? Two, how does a deploying router know that it is the last deploying router to be that this packet would go through? And after this, there will be either legacy routers or no routers along the way, and your packet will straight go to the host. And these markings should be kept secret, because if all the hosts on the internet know the marking, then what's the whole point of the marking? So what do you need to do to have these pieces of information? One, every deploying router needs to know the marking of its neighbors, and two, it needs to know whether when it sends a packet to the destination, there is a deploying router along the way that would strip the marking before it hits the end host. Because if that marking would not be stripped, then you don't want, you just want to verify and not put a new marking. Is that point clear? Because that's kind of crucial to what the approach is. If that's not clear, then we should not go forward. Yes? Huh?
I'm sorry, I said I was just stating a question.
Okay.
I have a different one that might come up later, though. Here, I'll turn this on. It seems like you have a bulletproof routing network. Like you're protecting against malicious hosts. But what if I have my own custom router and that's malicious?
Okay, very good question. This whole setup is assuming that routers are mostly not malicious. Because and you can argue that, oh, okay, it's a hard problem to solve in general, but you can argue then that the solution then is not useful at all. However, remember that you're not doing anything to the routing, basic routing. So when a router and the internet encounters a packet, it looks at the destination, forwards it. Until you have secured the routing, there's no way to protect the router in general. So in some way, it's like brushing that part of the question under the carpet and saying, okay, we first have to protect the routing, and once that happens, we'll think about how to protect the routing infrastructure. But in general, in this entire setup, we assume that hosts are malicious, could be colluding. However, routers in general are not malicious. And in fact, it turns out that the problem becomes hard enough that if you assume that an entire network of hosts is colluding, then also you can't do a whole lot about it. As long as stray hosts or a small number of colluding hosts are malicious, you can protect the network. But in a very general case, you cannot do that. And here, in this entire approach, our focus is mainly on practicality than perfect security. So practical security as against perfect security. So we need two pieces of information, and they should go in the routing table of a router. So everyone knows that the router actually has a forwarding information base that it uses to look up the destination. Yeah? So the routers actually have a table. Every time a packet comes in, they look up the prefix, the longest prefix match in that packet, and they map into that table that they have, and that table tells them what outgoing interface the packet should go in. So this is a result of your routing protocols. Your routing protocols run, then you get a forwarding information base, which is what I'll refer to as FIB throughout. And that table tells you how to route it to a destination. We need to enhance that table. And now that table should contain these two pieces of information. One is that prefix. So the router has one table, and it looks up the destination prefix and forwards the packet. Now a new packet comes in, and you first want to do a spoofing check. You look at the packet source address, and you look at your router, look at your prefix, the corresponding prefix in your FIB. And that prefix tells you what is the marking that this packet should have come with if the network that originated it was deploying it. Yeah? So let me try to draw this. So there is, I can just write here, right? So this is your FIB. And this is your prefix as of now. And this is your interface. That's all a router needs now, right now. So it can say 1.2.3, this class C address actually needs to go out on interface 2. That's your basic routing table. Are you able to see it or no? Because I can see it all over. So this is the key point. If we don't get to evaluation, it's not a big deal. I want to make sure that the key point is clear. Where is it?
This whole CV's got it. So,
Okay, so you have a prefix, you have an interface, and at this point, a router just looks at the destination address in a packet, says what interface it should go in, and it just sends it out, and that's all it does today. However, what I'm saying is you incorporate deployment status as a bit, saying it's deploying or it's not deploying. And let's say this is a deploying prefix, and you do a marking. So the marking could be letters A, B, C, D, for example. And that's the new information that's contained in your routing table now. So a packet comes in, it has two IP addresses in it. It has the source IP address and it has the destination IP address. It looks at the source IP address and it says, let's say the source IP address is here. And it says, for this source IP address, I'm not concerned with the interface because this isn't the destination IP address. This is just the source IP address. I say, okay, what's the marking for the source IP address? If the marking contained in the packet is the same as stored in the table, I say, okay, it seems like this packet contains the correct marking, right? Then I say, now I can actually forward this packet wherever it needs to go. Then I say, what is the destination IP address? Let's say this is the destination IP address somewhere else in your table. I do need the interface information because this packet is actually a genuine packet and I want to send it out. However, to decide whether or not to put the marking, I need to look up whether the deployment status is 1 or not for this destination IP address. Yeah.
Do you mean that you have to have a marking for each and every address in the network?
I will come to that point later. Yes. Yes.
That's not very scalable for a network of the size of the internet, for example.
Okay, so
And you have
if
to run it on every single router in the network. So
yes.
But it only needs its neighbors. It doesn't need
No, actually that's not true. It needs to, the prefixes are unique. So what it needs to know is while going towards destination, at least one router will be encountered. So as long as I know the existence of one deploying router, I'm fine. However, this information needs to be kept for every prefix. So that's a very good question. Think about a core router, a router that sits in the backbone of the internet. A core router typically has of the order of 200,000 entries in it, which is enough to route in the entire internet, right? So a core router already has information about every possible prefix in the network. Some might be aggregated, but that doesn't matter, right? For a core router, keeping this extra information, one happens to be just a bit, and the second happens to be, let's say, a 64-bit pattern, is not a big deal. However, for edge routers that use default routes quite a bit, they just know how to route to their close-by places, and then they have a default entry that goes in. This is a big overhead. And I will talk about how you might sort of relax the security it offers just to be more practical. Very good question.
yeah, I don't see why. I mean, it's one entry per fifth entry. So why did you imply that there's something subtle to it there about scalability? Is there something we're missing?
Um,
It looks like finite in size and small enough. And
it's finite, but you don't.
the updatability of it?
So okay, so it's finite. It's about 200,000 entry, and you keep it for everyone. The deployment status, this is partially deployed. That's what the assumption is. So while going towards the destination, you need to know whether there's at least one deploying router along the way or not. So if you see any, you just put a 1. Similarly, the markings, whichever path the packet takes to come to you, you only care about the last deploying router in that path just before it hits you and what marking they are using. So even though you're storing marking information for every prefix, but it might be repeated actually here. For example, if all of East Coast is coming to you via this particular router, then you're storing it for every prefix, but you're storing just one entry. Yeah. So the question now is, yes.
I wanted to go back to the table. And
Okay.
you said that those markings are supposed to be secret, but if you store a lot of them, just like if you get information from a couple of major routers, it looks like, I mean, you might be sad for the entire internet. You learn the markings, for most of the routers.
That's why it's important to not have the routers compromised in this. If your routers can't be trusted, if your end host cannot be trusted, that we are assuming, but if your routers cannot be trusted, then this would be hard. I don't know whether we will have the chance to get to it or not. The markings do change often. Like you might change them every 20, 30 minutes, and of course, every time you change marking, there has to be issues of how the new markings propagate in the routing tables have to be addressed. So you want to keep the overheads low, at the same time keep the markings secure. But in general, yes, if you manage to compromise a backbone router that has all the markings for the neighbors, then it is a problem. In general, you cannot afford to have routers compromised. And again, the reasoning for not addressing that issue is the same as, well, if your routing itself could be wrong in the first place, if the router is bad, then the packets won't get routed. They route the packets wherever they want.
But it also will depend on how they broadcast that marking information to all other routers, right? If it's incorporated into an existing protocol, that's not secure, that it's going to be a problem.
Yes, if you compromise a major router, and you compromise in the sense even when the router markings are updated, you get the new markings. And then, of course, this router will tell any end host on the internet as to what the markings of the neighboring routers are. I do have some simulation results here that show that because these markings, even though there's one marking for every prefix, however, every router is learning markings only of routers in its vicinity. And markings are per interface, as in, if you're using multiple paths, then markings will be different. Which means that even if you learn the markings, you have to be coming on the right interface to exploit the markings. And our results actually show that unless the entire internet host know about the markings, even if a router is compromised, you actually cannot misuse the markings as much as you would think. So, but that's a very good question, and hopefully I'll get to the simulation results, and you'll see that for perfect security, yes, learning any marking is bad, and our scheme doesn't prevent any markings from being learned. However, for practical spoofing prevention, many of such cases will get blocked out, because even if you know the marking, someone knows that marking cannot come that way. They just drop it. Make sense? Okay. So notice that earlier, a router would just do one lookup. It looks at the destination, it looks up this table, and says this is the interface it would go. Now, I've put two arrows here, which means that for the source address, you do a lookup. For the destination address, you do a lookup. So, which means that if your router is a gigabit per second router, it actually is getting gigabit per second traffic. In this scheme, its throughput would become half. So half of the traffic will probably get dropped or delayed. Okay? It does require an extra lookup for each packet. So that's the overhead, and that's the cost you have to pay. Now the question is, it's good that we have these markings in the table, but how do we learn the deployment status and markings? How do these fib tables get populated? That's the question. One way is you have some sort of a key exchange protocol where the routers go to either this, like an infrastructure of some sort, and it exists. You just go to the infrastructure and say, what's the marking of my neighbor? And there is some authentication that goes on, and you learn their markings. However, that means that you cannot really deploy that solution immediately. If your focus is on practical solution that can be immediately deployed, then that approach will prevent you from doing that. So here are the approaches that can be used, and that can be used instead. So the first approach we use is to tag along the marking and deployment status along the Bgp route announcements. So everyone here is familiar with Bgp? Border Gateway Protocol for inter-domain routing information. So this protocol essentially tells you, for this prefix, for this destination prefix, the packet should go, come from this path, right? And path meaning a domain or an autonomous system. In that, you can actually put the markings for, if a network generates a BGP route announcements and is deploying, it can put its marking and says, oh, I'm deploying, right? And this announcement will propagate in the internet and everyone would know about the routing. However, there are some issues to consider. One is BGP route announcements are often suppressed, which means an edge domain doesn't see all the announcements because the core router or the other routers they're connected to, sometimes their policies prevent these route announcements from propagating further. So at the edge, you don't see all the announcement. And that's part of the reason why the edge routers actually contain a few IP addresses there where they can actually route to. Beyond that, there's a default entry where they just send all the rest of the traffic there, right? So you can learn markings in general through BGP route announcements, but only the core routers will be able to do it. Most likely, the edge routers will not be able to learn them. Right? And as the announcements are propagating, you can say that okay, I'm the deploying router, so even though it's for the same prefix, use my marking, and that's how a router only maintains markings about its neighbors, not about the actual deploying one. So you contain damages in some way. The other problem is asymmetry. Yeah.
What if my neighbors don't deploy this marking scheme? So
when I say neighbor here, this is just the deploying neighbor.
Okay.
So you may be connected, you may be directly connected to two other routers, and then a third router is deploying. But that third router will say, okay, for this prefix, use my marking, and there is a deploying one. And the legacy routers, they just ignore these extra. You can think of them as options in a BGP route announcement. So whenever I mention neighbor, it's the neighbor in terms of the deploying router.
Okay. So that if, for example, I'm just a company, right, and I always go through the same internet provider, and I have to keep just one router in my table because this is the only path to the internet. But if that router is not deploying this marking scheme, then I have to give information about others, right, that are farther away from me.
Okay. So I think that this point probably didn't come across from what I just said. If you are connected to a router and your router isn't deploying it, then
my
your router
my router is deploying it, but the next hub that I always go through is not. So instead of keeping just one entry in my table, because this is just my default route, and this is always, I have to go through it. I don't have any other way. But instead of just keeping this one, I have to maintain information about other routes, because other routers that are farther, that 2 hops away from me, because and this will increase my table size, right?
Yes. So far what I have told you is, according to what I have told you, the tables of edge routers that usually just contain a few entries and a default entry, that will explode. As in, your tables would be the size of a core router, 200,000 entries, which isn't prohibitive, but we would like for that not to happen, and I'll discuss that in a little bit. Does that answer your question? So think of this as what I've told you right now, in the worst case scenario, gives your router 200,000 entries to look at when it's making forwarding decisions. That's the worst case scenario. Right? In fact, the last study that looked at the BGP table routing table sizes, the FIBs, said it was about 180,000 entries. So it's not that big a deal. However, we would like to avoid that overhead if possible. And remember that this is only a concern for the routers very close to you. The routers that are farther away, which is the backbone routers, they are already maintaining information about every network prefix. So all they are doing is really keeping an extra bit and a marking. That's all. But for edge routers, this could be an issue if their lookup isn't fast enough. But really think about it. The fast routers, the multi-gigabit per second routers are the backbone routers, and they have to be because they're aggregating traffic from all sides. Your router, which is the edge router, is a much cheaper maybe $20,000 router as against the $500,000 router that the core router would be. Is much cheaper, but if memory is not an issue, you're keeping this larger size table, let's say 200,000 entries. But lookup isn't going to be such a big deal because you're also not getting traffic from thousands of other sources, right? So you're not getting a gigabit. You don't have to route at gigabit per second speeds. So if you can save, if you can just have extra entries, your lookup will be slower, but at the same time, you won't be dropping packets or anything. But we would like to reduce that overhead as much as possible. So the point is, because BGP route announcements are suppressed and there is asymmetry in the internet, which means that you would see a route announcements comes a certain way, and that tells you that to reach me, you can use that route. However, that doesn't mean that they will send you packets from that route using the same route, right? So this could be, let's say this is your topology. A route announcement is generated from here, and it takes this path to tell this router that to get to me, you can take this path, right? So when this router sends the packet, it will send packets this way. And that's all the BGP announcement is trying to tell you, right? However, this announcement doesn't say anything about how this network will send packets. So this network, so this is the announcement, and this is the actual packet. The packet could traverse this way, right? The route announcements traverse this way, which means if you are sending any data to them, if this router is sending any data to them, it will take that path. But the route announcement says nothing about how the announcer may send data, which means your route announcement, your information that you keep in your table based on BGP route announcements may be wrong. Does that make sense? Is it intuitive? One is you may not, as an edge router, you may not see the announcement, and I see that as a bigger problem than the size of the table, right? The second is you see announcement for a destination. However, that announcement says how you may send packets to me. It says nothing about how I may send packets to you. So the classic problem of internet asymmetry basically prevents you from learning these markings and storing in your table. Is that clear? To get around that problem where your markings are incorrect and you don't even know about it, right? In what cases would you not know about it? So here's another case. You have this asymmetry. However, this router under consideration is this one. It sends packets this way and it receives packets this way. And let's say these are the deploying routers. And they use all use different markings. So when the announcement comes, this is the marking it would learn. But when the packet comes, this is the marking it would contain. However, at this router, you don't even know that the asymmetry exists because as far as you are concerned, the packets are going out this way and coming this way. So there are two problems. One, your route announcements may get completely suppressed. Two, you may learn incorrect markings for your neighboring deploying routers, but you may not be topologically situated to actually find out that they are not doing it, that the marking you learned is wrong. So bottom line, even though when you have it, BGP is good, when you don't have it, you need some other mechanism. And these two mechanisms, the recursive router challenges and host probing, accomplish just that. So I think I already talked about BGP route announcements. So let me now talk about what recursive router challenges. Essentially, when a router receives a marking it doesn't know, it consults its packet, it gets a packet, it does a lookup in its forwarding information base on the source address, and the packet marking contained in the packet isn't the marking it has stored for that source IP address, for the source prefix, then it cannot, based on the information we have so far from BGP route announcements, it cannot rule out that the packet is necessarily spoofed, right? Because this marking could be incorrect simply due to asymmetry. In which case, it needs to issue a challenge to learn the marking actively. No, I'm not able to figure out if that point made it to you or not. How much more time do we have? We should end, right? So let me not go into the details of these techniques because we are out of time. I hope what I have managed to communicate to you is one, what IP spoofing is, how it is a problem, how it can be used to launch denial of service attacks, but prevention of this would cure or would curtail a lot of denial of service attacks, but not all types. And routers can actually prevent IP spoofing by simple extensions to the routing table that they're using. However, how you enhance the routing table to incorporate this extra information is the basic question. The first way you could do, and that's the simplest and least overhead way, is to use BGP route announcements. However, BGP route announcements are very good for doing deployment status because when you have a destination IP address, you send it that way, and the asymmetry problem doesn't arise in the announcement for deployment status. However, the routers may learn incorrect markings simply due to asymmetry in the internet, and depending on how far the asymmetry is from them, they may not even know that the marking they have stored is incorrect, right? So there are other approaches that one could use to ensure that the markings you store are actually genuine. And the basic idea of this approach is to issue a challenge to the router until you and get a reply from the router, so it would contain a marking that was contained in the packet you saw. So even though you don't hold the packet, you let the packet go, but you at least verify the marking and you then update your marking in your table. Okay, so I don't think we would have time to go through various cases of this. It turns out that this approach would also fail in certain small number of scenarios. Question?
I had sort of a fundamental question about this approach. So you said, like in the beginning of this talk, that if we just do ingress filtering, it does not provide incentives. But if we do this marking technique, it does for the claim, or
Yes, yes,
okay.
yes. That's a good question, actually, because that's fundamental to why you would want to incur additional overhead. See, remember what we are doing. We are doing ingress filtering, and we are doing everything else. We are doing an extra lookup on your routing table, and you're having to generate this information in your routing table. Why would you want to do that? Because the problem is still the same, that if everyone was deploying ingress filtering, you would not have a problem, right? Because then you almost like form a shield in the network. If some people are not deploying it, that problem is still the same, partial deployment. So how are we providing incentives? So I'm sorry that this point didn't come across earlier, but when a router verifies a marking, what does the process of verification mean? It looks at a source address in a packet and it says, oh, this marking is actually correct versus not. I expected this marking to be something, so either the marking isn't there or the marking is an incorrect one. Then it drops the packet. What that helps is, if you are deploying, if you are a network who's deploying, which means your packets would travel to the next deploying router marked, and someone else is trying to spoof you, that router, if that someone else proceeds encounters a deploying router, their spoofed packets will not make it. Let me try to say that again. So here's a deploying network, and there may be other non-deploying networks in the middle. And here's Trudy. Here's you. So you mark your packets, and the router verifies the markings, and it sends them to whatever destination you're sending them. So your packets are going fine, just as they would in the case of ingress filtering. In fact, you're incurring extra overhead at the routers, right? Because you're verifying the markings at every step, stripping off the marking, etc., etc. However, what ingress filtering didn't give you is that when Trudy tries to generate a packet saying it's coming from you to whosoever it wants and the packet, this goes to this or any other deploying router in the internet. Let's say it goes to this one. It says, oh, your packet doesn't contain the marking that I expected from Trudy's packet doesn't contain the marking it expected from you. Drop it. Which means I am not just doing ingress filtering and putting a marking for the benefit of others or in general. I am being given an incentive to put this marking because if someone else tries to deploy me, to spoof me, and they encounter a deploying router, they will get dropped. So hence the incentive point.
I thought the incentive should be on the side of the router. What is the incentive for the router to implement that? Obviously, if I'm sending the packets, I would like to mark them. I'm going to keep.
Okay, so let me ask you a reverse question for that. What is the incentive for a router to do routing? Why do those poor things, they cost pretty close to $500,000. Why do those poor things exchange all these packets on the internet for your goodwill? No, there is incentive for them to deploy because the ISPs are getting paid to carry traffic. So the routers have no problem deploying it. In fact, if you could convince them with minimal overhead, they can actually accomplish this. A lot of ISPs would like to have this functionality, right? So I didn't get into this, but this also, the recursive router challenge also fails, and there's another approach, but at the end of it, we can cover all cases. And we don't have time for any of this. So I guess we'll skip evaluation. The point of the evaluation here is that, one, under partial deployment, we can actually prevent spoofing. And to what extent you can prevent spoofing at what deployment percentages. That's one aspect of the evaluation. And does marking learning actually happen if you try to keep the size of the fib table at the edge routers just as short as it would be in the normal case? It turns out that you can learn markings in that case. However, how much can you learn? And even if you exchange the learned markings with everyone, let's say you set up a website and you show the markings to everyone and charge some money for those markings, it turns out that you cannot exploit the learned markings as much as you would like to, because the markings have direction information in them. So just learning the marking doesn't help you exploit all the routers. So I'm sorry we couldn't get to the end of it, but I hope I was able to communicate some of the basic ideas here.
We never got to how the markings evolve. Is there any relationship between one marking and when it evolves into another marking? Is there a notion of distance between them? Or is it a random change? You see, the idea is that if there is a notion of distance, by drifting slowly, it phases out the old one. And then you have a threshold scheme where I don't expect the marking to be exactly the same to accept it, as long as it's within a delta. And then you have them drift slowly over time, and it would be very clean.
Yes. So some of the practical considerations, again, that we didn't go into is, what is the format of the marking? Where should it be put in the packet? An easiest thing to do would be IP options, but that means that routers actually don't process IP options in the fast path, so you actually would go in the slow part. That is one aspect. The other is, so marking format as in size. The bigger the marking is, the harder it is to guess. Remember that we are not using cryptography. So any marking you put can be guessed. So the longer it is, harder to guess, right? Location of the marking is another thing. Third is changing of markings. And change of markings could be you just randomly switch to another marking and the router does whatever it did earlier to learn the markings. It does the same thing. That's one approach. The other approach that has been used in some earlier work is the notion of hash chain. So the router actually sends you this hash chain ahead of time, and it has essentially information about, let's say, 20 markings. And it changes from one marking to another, and you can still verify up to 20, at which point it explicitly sends you another hash chain. However, this notion of delta would be interesting, but I haven't seen anyone.
We need to talk because you can actually, you don't need to have the reset after 20. You could have an open-ended hash chain.
Okay, so I'm not that familiar with the, yeah.
You know, you're thinking of a hash chain in a certain way, but there are ways of making the hash chain open-ended.
Yes. So that would be basically the issue is that since markings can be learned, you want to minimize the damage that can be done from the learned markings. So you want to change your markings. And there are pretty slick approaches where once you've learned a marking, they can change within certain parameters and you can still basically know.